So for the last talk, we had Haojie Ren, who's going to talk to us about LP dimensional self-conformal measures. Please.
Thank you, Sophia, for the invitations for this Budapest very beautiful city. Like, I very enjoy to come here every time. And I had to say my English maybe pronunciation is something also. If you can't understand what I'm talking about, please interrupt me and maybe you can just choose to see the picture, but I can ask question anytime.
I don't think that the language will be the problem.
And I also wanted to thank Pablo and since Usuki, I learned some how to study actual dimension from them. They are very friendly. And I wanted to talk some the project we are working on together. And basically, I wanted to study for the self-conformal measures on the R. Basically, the same setting with every report, and we wanted to study the LQ dimension. And by the way, this one is the LQ spectrum. I will give definition later, and we wanted to on the exponential separations assumptions. Basically, we have give these assumptions definitions twice. But I will give a section at a time, but very quickly. And we wanted to know if on the exponential separation assumptions, of course, we assume the support of the unit for the singletons. So we just give a formula for the spectrum with this the 0 point of the pressure functions, -1s for every Q. And I will go to from the line from the Shmerkin result for linear case, and then the Usuki's works on the Möbius dichotomies, and then I'll work with analytic dichotomy theories. And we will state the theory what it is, and we will show why the bad case. We could have two cases called linear pairs called the bad case. We will show how to avoid the bad case under transversality assumptions. Then we'll give a non-trivial examples for such an example satisfy the transversalities. And now let's just give some definitions for people who are familiar with the LQ sightings. We wanted to use U for the intervals such as zero bonds, and find the finite collection of analytic IFS, of course. We assume the derivative strictly less than 1 and strictly positive as we always split. And let P be a positive probability vectors, case attractors, and use the self-conformal measures. And now we can define the LQ spectrum. And basically, DM is what I think Joe talked about, is a partition of the intervals, partition of R to the scale at 2 power of negative n. And then if the sum of I from these partitions and consider these maps with the power over Q, and take the log divided n with -1. And this limit exists by the subadductive. And I think these people are very familiar with these things. But just to remember these notations basically. And the LQ dimension is divided by the spectrum divided the Q divided the Q -1s. And we are the 0 point of the pressure defined in this ways. And you saw I from lambda n's with PIQ as in this definition as we used very importantly. And divide the strabbators of this maps, 0 1s, the power of negative s, and sum them together. This is the 0 point. So this is the basic sightings. And I think people should maybe some people are very familiar about these things. And the question is, we already knows that this is the right side is the up bound of these dimensions. Since they are in one dimension space, Q -1 is always up bound. And this is not hard to finish. Since according to the definition, you just divide sum all of the symbols with a PIQ together, so you can easily to show it's also up bound. And the question is, under exponential separations, can we assume this also this other bound is equal to this LQ spectrum? This is basically the questions. Of course, in the nonlinear setting, you need to assume also additional, like I already did, case not a singleton, and under exponential separated, when we prove these things, this is basically what we wanted to know is the basic questions. Sorry, I didn't know us. And let's just, since the workshop name is the Dimensions of, want to recall the results from Michael and Ariel's. They are basically the same if we consider the measure dimension, if we assume the dimensional separation conditions. Basically, we can choose this formula hold for the dimension. So for the dimension, we have these sightings. I think we have recall this result. This is the third time that I still want to mention this result is very important. Of course, later Joe told me result with errors about the conformal sightings in the plan. But the dimension drop actually will happens with the LQ sightings, not like the matter of sightings. And I will give examples and explain later. Okay. Now let's just recall the result of Shmerkin. Shmerkin, in his very famous papers in the 2019, he studied a linear case. If you, I would like just write down the formulas. Phi ix is equal to lambda I times x plus ai. And under these things, you can just write clearly of this 0 point of pressures is this equation. You can write clearly this way. And Shmerkin proved on exponential separations for every Q this formula proves. And but in the Möbius sightings very recently result from the Shunsuke Usuki's, and we will talk about it here. So, and in these sightings, we consider metric AI from SL to R, and PI is also probability vectors. And in these sightings, we need also assume need to consider a condition called uniform robotic. Basically, they are saying that the projection line. Sorry. This is the projection line. And you can find some intervals. Like phi I is this is AI. So this AI is acting on the projection line space is strong contractions, like come back to the basic sightings of the and contracting sighting will go back to the random work, something like these sightings. And the pressure function, since the acting contract to be a metric G from SL to R, the contraction rate is the norm of the power of -2. So here we need to change the derivation to this contraction rate. This is a defined new pressure functions. So also, and this is that theta tau A is the 0 point of the pressure functions. And Usuki's in this sighting, even still very the SL2R is even still very close to the linear sighting. Unfortunately, I really found very complex examples. Since even you assume they still have a uniform robotic contraction sightings and strongly defantings, even assume like basically you can consider as something like the potential separations assumptions. And under the standard assumptions, Usuki said, if you find two matrices and they share the same fixed point, and you can choose the probability vectors, of course, and make the probability in this matrix very, very sum together very large, which means the probability I0 and Z0 sum together very close to 1, which means you basically you only need to consider the two maps, ignoring the third maps. And with these assumptions, if I impute the super large, then the formula fails. It's very weird conclusion, which means LQ dimension is more sensitive compared with the Meyer dimensions. Why is this? Since Meyer dimension you can ignore a point is Meyer's dimensions, but LQ dimension point have a strong influence for the LQ dimensions. This is a different part, but don't worry, I will give you examples to the analytical compression sightings and examples. So if this formula fails, still wanted to know what is the right formula for these sightings, and Usuki give a dichotomy theories under strong defining conditions. Basically, as I said, you can just consider as the dimensional separate conditions. Worries and A is the uniform metric. The system is the uniform bodies, is basically like uniform contractions, and under strong defining condition, uniform exponential separated and basic standard descriptions is that only two cases will happen. The first cases is a good cases. For every Q, this formula is what we want. This is a nice formula. But unfortunately, if sometimes we can find a Q0 is super big, after Q bigger than the Q0s, we can find a linear growth. And these two saturation, only one saturation will happen. And this is the Usuki result. And very questions, I think I will read the questions in the Balassis and Istefan and Sasha's paper. They ask questions whether understanding the Usuki's economy zeros will and analytical conformal questions, the major questions, even Usuki writes similar things in the papers. And our results was Shmerkin and Usuki's. And the sightings, basic sighting with the theorem areas, identify the finite collection of analytic IFSs, that is the intervals and positive probability vectors. Assume exponential separations. Then, if the K is not a single term, exactly one of the single, exactly one formula happens. And this is basically extension the Usuki result to the analytic sightings. And I wanted to give an example. This benefit still happens. This is an example as being mentioned in the Istefans talk this morning. Basically, it's the same examples, but I think since we consider analytical sightings, it's a good example to do the projection, not consider projection in real-life space. The key point of this example is that the F1 and F2 share the same fixed point, but F3 have another fixed point. In these examples, this still can satisfy this strong exponential separate conditions. I think Istefan has to give definitions basically. Even you give a exponential separate condition, very non-trivial examples. It's very nice examples. And you do the same thing. Basically, give the first and the second maps the very big mass very close to 1 divided 2. And the third just don't give too many mass, but you still put some mass to it. Then you find the formula fails. And I wanted to show why this, give an explanation to why this fails. Basically, since there is a shared the same fixed point of F1 and F2, and you take the row is bigger than the derivative of F1 and F2s. You consider the ball center as zeros and with the ratios of rho n. Here we can take very close to 1. And to just serve the balls will include such a balls in here, estimated here. We were including all the maps by I from the 1 to n. Since you take the row is bigger than the maximum at vectors. Basically, you are taking this with and then you can find something. You can find this mass is very big. Why is big? Since you consider mass, the mass is in the 0 point. The second thing is you need to do the calculation of the LQ spectrum. So you need to sum, or you just sum mn is made a scale like the drawing. So you can, since you can find two intervals to cover these balls. So when you sum these things, basically the mass of this part is bigger than the 2 times T0 and the square was power of NQ. Then you take the log according to the definitions, you take the alpha equal to these ones. Since this one mass is very close to 1, and this we fix. And this will go to, this can be very small, so this will fails. So the mass they have found this respectively as P minus 1. And the third part is the cylinder. You still need to prove the LQ spectrum is strictly less than the 0 point of the pressure. Basically, you are calculating the pressure is something you're calculating the symbols of separatedly. This is why the 0 point of pressure is upper bound since you are calculating separatedly. Then you calculating the here's, and this is 2 of n. You compare with here. This is here. Here is to have the power of q minus 1 is more bigger. So this make you can find the pressure. The 0 point of pressure is strictly bigger than the LQ spectrum, and is here. Why is come to compare here and compare here's? Then you find the increased part, and this increased part, well, when Q is very big, you do these things here. The institutions basically is a lot of the mass concentrate on this point, and but if you the pressure, the 0 point of pressure is calculated by separated these. These are the very different ones considered. You study the LQ spectrum is consider all the concentrate on 1 point, but the pressure function, the pressure is just consider separated these. So the reason. And the question is in the Usuki's papers, he didn't find non-trivial examples to show the good case it happens. Later we are sure to prove that you can see why it's hard to find a good examples compared with the bad examples. But in our joint work here, we wanted to see we can give under transversality assumption we can give assumption give a theory to show the good case happens. Basically, we consider real analytic parameter families. And the T is the parameters, and this is analytic maps. And the definition of facility is the standard classical definition where you see CT is strictly bigger than 1. You find such a constant, then for different choice, if their first symbols are different, then the parameters of this mass is something less than this part. I think that this is a standard assumption. You won't go back to Somiaka's times. I think that Balazs and was wrong, and I don't have the papers study the value of a dimension very general sightings with these assumptions. But here we give a result for the LQ dimensions, and with our result set, if consider such a families satisfy the transversalities then for almost every point, and at the same time for every Q, the case where it happens. This is basically something we can give a good example. Or use this to give another examples. And to prove this, we definitely should use our dichotomy theories. How to prove this? We first need to study the structure of the value of the bad case. We find a structure, then we'll shoot according to the structure, the bad case will happen under the transportation assumptions with only a zero value part. Then we can use our dichotomy theory to show the good case almost well happens. And I wanted to write down another. This is for parameter families, but just you wanted to know for this, I wanted to write down the more strong conditions, but it's not compared with the part. Something like if I wanted to write more strong list of the questions, I wanted to know is and even this code, we also could assume that the case happens. But here, this is in the if. It's basically compared with has been proven by Stefan and Sasha and analysis is too strong. You can prove in these items this good physical happens, but too strong. I so we wanted to present here. So that if you can someone can prove this is generic and some things you can use, you can get the good case what happens. So it's, I think this is I wanted to additional to share to this since I listened to this example. And with this in the analytic sightings, we can give a non-trivial examples. Why is non-trivial things overlapping what happens in these sightings? Basically this is a nonlinear examples. Parameter is a t in this part, and this permutations in this part. And how to prove this? Basically, if epsilon equal to zeros, it's complicated to the Bernoulli convolution families, and then you can. This is this transportability. I use a more strong transportability in the paper of the Solniak and the Paris papers, and this is stable on the C1. Then we can show in the nonlinear sightings satisfy the transportability assumptions in our transformative result. Then you can basically show this. This is our non-trivial examples in the nonlinear sightings. And we can give it I think check the time. Okay. And I want to prove strategies in the linear case. And in the rest, I wanted to show how to prove the minimum of the theories. And but for the transportability theories, also spend a lot of time to prove this. But we don't want to give the proof today. And we wanted to simply start it from the linear case. First things, I want to give the Shmerkin's argument in the linear case as mentioned in the first talk. Something like philosophy very close to the Michael's papers in the very famous for the Meyer dimensions. And that's in the lambda in the Bernoulli convolutions. We consider the differential point Q. Since tau is concave and you can show that differential point where is the dense point, and this is the continue with a Q. So you can just consider the point. Q is the differential point. Assume that this fails, and UN is the first n terms of the sum of the laws, and they have convolution structures. I wanted to write down these notations for measures. And this is for the L-Q norm. Is a sum. I just wanted to write down the notations for people to be able to remember this notation where I used to. Oh, sorry. This is alpha norm. Our goal is to shoot for large R since we have a strong exponential separations. So you can find R separated, then every point will separate it like the point of the Vn. And then you only need to shoot the alpha norm at the scale of R plus 1 and times m. So it's basically the same what we are looking for, the alpha spectrum of this part. And if we are going to shoot this part, and but the reason is why we only need to shoot basically the same philosophy with Michael's papers. If they are unseparated, then you can do the calculating right. The probability is 2 power of negative n's, and then you have the 2n points, and then you calculate the norm with pressure 0.1 pressures. Then you can shoot this code. And very importantly, for fluid this is what the Shmerkin's result called the L-shape flattening theories by the conclusion part. Basically, if something like if you give it a tau, positive taus, then if the mass has a decay according to with the small decays, then convolution with the probability measures, you can find a non-trivial. Here is epsilon even is very small, but here you can get a new decays. This is important. And to prove this such a flattening theory, basically you use the Shmerkin's LQ inverse theories, and they have some additive compensation ideas, but we don't want to claim here. But so just this can be used as a tools. And the proof philosophy, the proof is very it's basically the philosophy is very similar with what the Michael did, but in the LQ sightings, first you give intervals in the DM, your restriction to these intervals, then you scale it to the normal size. And we have to estimate the first part is use the convolution formula to give an upper bound. And the second is to just use the convective of the Q just to give a lower bound. And I don't want to explain why the formula has rather you just include it to see. First, you need to split this as the intervals in this part between the two parts. The first part is that have a good decay part. The second is the rest of them. And from these formulas, and we wanted to give the from upper bound, we divided this part into the two parts. One is a good part. For the good part, we can use the flattening theories. In flattening theory, you are non-trivial decays from here. This is non-trivial decay. Here, this is basically this, and here is basically the level in this part. And so you can find a non-trivial decay in this part. And you can then this the sum here for the interval I from F can be ignoring. You just consider use these formulas, then you can get the mass of the mass of the bad part. This mass survive over the big mass. Our goal is to shoot the big mass. This is called survival part. And this we call for the I from the survival part. And you can use a second formula. This formula is from the UN. The set you can decide the scale with R plus 1 times M. You can need to only consider the sum of this the mass of restriction intervals and give us more dedicated the norm of this part. Then you use these formulas and you can get a lower bound to calculate this bad part, and sum them together so you can get the lower bound. This is basically what we are looking for to shoot here. And now, I don't want to give more details about another math proofs. Now, just give some explanations why Shmerkin's proof in the nonlinear society, what is new difficulty? The first part in the convoluted convolutions, they have convolution structures. And you can do the partition of the intervals just according to the point as Vn. Vn's, they adjust the point in the interval U. But now, in the analytic setting, don't have such a partition since the function space in the infinite dimension things, you don't have a partitions. But if you wanted to build a partition in the infinite dimension, since it will make some troubles, you need a very nice partition like in the Haojie space. And another difficulty part is convoluted convolution have a nature convolution structures. But if you consider in the nonlinear settings, you don't have such a convolution structure, you only have such actions. So the proof strategies, so in our main theory, the proof strategies basically is we only consider the differential point Q's, which makes the alpha spectrum strictly less than Q minus 1s. And we consider the gender transformations portion when Q is differentiable, you can see alpha is a different derivators, then you can transfer to here. If torsion is positive ones, then we will prove this formula holds in these items. If torsion is zeros, then you can find the bad part. This is the bad case. And then we will use some argument from the errors and also some arguments from the Usuki proofs to show these things. The first thing is how to understand the torsion, Hausdorff. And since Q is tau is differential at this point, the Hausdorff can have exactly formulas. This is what we actually need. What is the meanings? We wanted to calculate the mass for such an LQ norm. Basically, you can use a pigeonhole to show you only consider intervals have same scales at these levels, and how many numbers divided by the Hausdorff. Hausdorff decide the numbers. So since I will explain, so one of the technique is to shoot if the tau star is the positive ones, and we can prove this formula holds. Why we need, depending on why the bad case or the good case in the beta tau star is the positive or zeros. So since we used to pigeonhole theories, pigeonhole principles very, very, very frequently times. So if you use one time of pigeonhole theory, you will lose very small. You will lose very small mass. You will lose the mass using numbers. But if tau stars is positive part, then you can even lose this small epsilons. You still can left some tau stars. This is why we need the tau star to be positive things. And if tau star is a zero part, you have a linear tails. And I check the time whether I needed to do the. And just very quick to show the proof why the linear case what happens. If tau stars is zeros according to the Lagrange formula, this is the differential point, then you can have these formulas. And since the differential point is a dense point, you can choose another point Q1, and write alpha ones is the derivative of the tau. At this point, then you have these formulas. Why this formula happens since this is a tau Q, this is growing this way, this is Q1, this is Q2. Oh, sorry, this is Q2. This is the Q0, this is Q0, this is Q1. Then this is this gravitators is now is decreased. Basically, from first from here. From here, you can prove this out from here. Then you use a formula, bring here to their place. Then you can get this is a less than 0, since the gravitators become more and more decrease. So this part prove this is less than 0. But we already said, according to the formulas in this part, this number means this top stars means the numbers, because the numbers always non-negative, so it's a negative part. Then you can shoot this top with alpha 1 equal to alpha 0, and this is a 0. So basically, use this way to shoot this linearities. Well, happens in very easy, very short proof. The difficulty part is to shoot the top star is the positive how to prove these things. And this just to remind you strategy again. We only need to consider the point Q is a differential point. And if tau Q equal to the Q minus 1, this just you don't need to prove anything. But if it's strictly less than Q minus 1, then we already shows people that tau star is 0, the linear pairs happens. But in this case, this is what we actually need to extend proof. This part is very important part. So now we are proving things how to handle the two difficulties. One is use observations, Erdős papers. Basically, Erdős paper says we can use the polynomial to approximations of the analytic functions. Basically, to make use, you don't need to consider the infinite dimension space. You only consider finite dimension space. But why we can do it this way? This is a very important observations. You consider the symbols to two parts. You can fix the second part and choose different first part. Then you can do approximations. So you can fix this, and then here you can use the polynomial to do the approximations. So, but in the LQ sightings, our Erdős observations and use these observation papers to study the entropy sightings. But if you study LQ normal sightings, this is our papers to do. We need this is we use the observation of the strategies and the Usuki and the Shmerkins to prove this. We only need to transfer our theories, basically in the argument of the Shmerkin's argument, to transfer to study LQ flattening theories. In our papers, we wanted to give a more general citing of LQ flattening theories. We don't need to consider the space of polynomial space, or even consider a doubling metric space, and we only need to consider them, or we consider more general actions from y times u to the r. And our LQ flattening theory basically said if we have a since it's a y is a doubling metric space, you can build a nice partitions by the works by Karl Marx and other papers. And then you can if this case happens, then you can have a flattening theories in this part in a very general citing. We build the flattening theory in very general sightings. And then we can apply our citing to the polynomial case. Then you can get LQ flattening theory in the polynomial case. Since we have the approximations to the analytic function to the polynomial functions, then we can get what we want. Basically, this is already enough for us. The difficulty is one of the next things is to prove the LQ flattening theories. And to prove the LQ flattening theories, you need to face another second difficulty part, is you don't have the convolution structures. So you need to use the observation of the linear local linearizations actions in these sightings. Basically, as mentioned, it has been we can go back even to the Somiaka and the Hockmans and later to the Basis papers, the Hockman, the reports, and a lot of uses and arguments. With these visualizations, you can, with the restriction to a local part, you can find a convolution structure, then you can use the Shmerkin's and inverse theory to do these things. So to do the basically is to find the L2, to use these things, you need to do the difficulty part is to find some sightings to some restriction to a restriction of local size. You need to transfer the global property to the local properties. And this is our extension of Usuki's L2 porosity lemma to the general sightings and even to the high dimension. This part we are trying to extension the high dimensions. I think it can be useful to start the high dimension cases. And it said if you have a global properties, one is the pay of the actual one, and second is assume something fails. You don't have the flatness. The proof is strategies by the contradiction part. You assume you don't have the flattening properties. Then you can find a local intervals. One is in the metric space and y, another is a small intervals of I in the scale. Then you can find then under the action of x zeros, you can have the decays, then you can find make these two property localizers. This is the global properties. Then you can find a small intervals to make such things localizers. Then you can get the conclusions and finish the proof after flattening zeros. I think I've been done. I think in last talk is better to maybe walk a few minutes to have time to. And I think if you give every details is too complicated. You have a lot of applications of Technion easily. And since it's 16 minutes, I prepare some details. The details just to make people a little confused. I just quickly because I want to do that now with I think it's enough. If you have interest in something, I think we are writing the papers. Discussion to write something. I can talk later. Thanks.
Give me the questions.
So you have these bad examples where the alpha spectrum doesn't satisfy the accepted formula, and I think you mentioned that it would be harder to construct good examples.
Yeah. That's
which are not subsimilar. So can you say a bit more about why it's difficult to construct?
It's a very nice question. I think this this is a good case. This is a good case. The good case needed to say we need to tau stars to be positive. It's easy to choose that is equal to 0. Find examples is 0, but it's very hard to find examples to give some conditions. Here I'm writing one of the condition can void this condition. From these conditions, from this very strong separate condition, you can choose tau stars positive. But if you give it's hard to find example satisfy this assumption for some part. I think it's difficult. So we try to use the translative argument to find a perfect example. But it's a good question to ask what is something gentle and nice solution to make this be positive, but I'm not sure example. So simple difficulty. Since if constantly with zeros, you only can get a lot of information on a point. They are trying to in a small interval have too many maths, but it's hard to get some information in a very mathematical way to show some condition to avoid these bad cases. So if someone could show this, is very nice.
Okay, thank you.
So you really need the transversality or some higher order transversality K for the transversality would be also sufficient to show that for typical parameters the P star is positive. So the higher order, not that type of transversality what you showed, but the higher order, basically which says that R, the Lebesgue measure of the back parameters is R to the power 1 over n or something.
Yeah, we use the first orders, and but you can just use first order. You need to show the bad intervals with the finite intervals. Then we can use this to avoid to show the bad points. It's very similar. The fractals sightings. Why we can show this is we find the structure. We under assumption the bad case, and we find the structure of the measures. We know structure of the measures, so we can use the structure to show the bad point. It's very similar. But to show the bad point very similar with the facilities.
Yeah.
So then we can use our dichotomy theory to show the good case happens. This is the key. Thanks.
If there are no other questions, then let's thank Haojie again.